So now we have all these different laws for exponential, and I'm going to focus momentarily on differentiation. So we have the derivative of e to the x is e to the x, and we have the form for the chain rule. Now we have four functions that we would like to differentiate to illustrate how to apply this formula. First, we want to differentiate y is e to the x over 1 plus x, so I differentiate y with respect to x, and I'm differentiating a quotient, so I differentiate using the quotient rule. We start with derivative of the top, so that's derivative of e to the x, which is again e to the x, multiply by the bottom unchanged, 1 plus x. Then I subtract the derivative of the bottom, which is 1, multiply by the top unchanged, which is e to the x, and I divide by the bottom squared, so I get 1 plus x squared at the bottom. At the top, if I multiply things through, I get e to the x plus x e to the x minus e to the x, so that after cancellation, we get x e to the x divided by 1 plus x squared. Moving on to the second function, we have y as a function of u. So I'm going to differentiate y with respect to the variable u, and it's a product of the function e to the u squared with cosine of u. So I'm going to start with the product rule. So the derivative of y with respect to u is the derivative of the first factor, e to the u squared, multiplied by the second factor unchanged, cosine u, plus first factor unchanged, e to the u squared, multiplied by the derivative of cosine u, which is negative sine u. Here, I still have to calculate the derivative of e to the u squared. That's, I have the function u squared plugged inside the exponential function, so it's a composite, and therefore I'm going to use a chain rule. I get derivative of the exponential evaluated at u squared, that's e to the u squared, but then I have to multiply that by the derivative of the function inside, derivative of u squared, which is 2u. So I get 2u e to the u squared times cosine u minus e to the u squared sine u. In the third case, we have again a product of e to the x with ln of x. So we're going to use again the product rule. Derivative of the first factor is e to the x. I multiply by the second factor unchanged, so I get e to the x times ln of x. And then I add first factor unchanged, e to the x, multiplied by derivative of the second factor, derivative of ln of x is 1 over x. So I get e to the x multiplied by ln of x plus 1 over x. Finally, I want to differentiate cosine of e to the pi x. Here I have the function e to the pi x that is plugged inside the cosine function, so it's a composite, and I'm going to use a chain rule. So the derivative of y with respect to x is the derivative of the cosine function, which is negative sine, evaluated at the inside function e to the pi x, so I get negative sine e to the pi x, and then I have to multiply by the derivative of the function inside, derivative of e to the pi x. Now e to the pi x is itself a composite. I have the function pi x plugged inside the exponential function. So when I differentiate that, I obtain derivative of the exponential, which is itself, evaluated at pi x, that's e to the pi x, and I have to multiply by the derivative of pi x, which is just pi. So I obtain negative sine of e to the pi x multiplied by pi e to the pi x. Now we're going to look at application of this other formula, the integral side of the same formula, and apply that to calculating various integrals. Starting with the integral from 0 to 1 of x e to the x squared. Now so far, even though in this course we're going to see a lot more techniques to calculate integrals, so far what you know from Calc 1 is how to integrate certain functions straight from formulas that give you antiderivatives, or the other technique that is available to you so far is substitution. So here, if you don't know directly the antiderivative of x e to the x squared, that suggests that probably you should use substitution. Substitution, the typical case is that you have a composite part, and then you take for the new variable what's inside the composite part, and hopefully you should have a constant multiple of the derivative of that appears to get your du. So in this case, we have x squared plugged inside the exponential, so the natural candidate for the new variable is u equal x squared. If we pick that u, then du is 2x dx, and what we have inside our integral is not quite 2x dx, it's x dx, but that's 1/2 of du. So I'm going to replace x dx by 1/2 of du, and e to the x squared by e to the u, and we obtain 1/2 integral of e to the u du. Now when we use substitution for a definite integral, we normally have to change the bounds. So here they didn't change, but this is more of a coincidence. In fact, here the lower bound of integration is 0 because when x is 0, u is also 0. To obtain this 0, I plug x equals 0 in the formula for u, and I happen to obtain 0 again. Similarly here, to obtain this upper bound, I plug x equal 1 in the formula u equal x squared to obtain the value of u. Again, I happen to obtain 1 again. So we obtain 1/2 of the antiderivative of e to the u, which is e to the u itself, that we evaluate between 0 and 1, applying here the fundamental theorem of calculus. So we plug u equal 1 and u equal 0 and take the difference, so it gives us 1/2 of e to the 1, which is e, minus e to the 0, which is 1. Looking at the second integral, now we are looking for an indefinite integral, so just antiderivative of e to the 1 over x divided by x squared. Again, so far we don't have a lot of tools available. Substitution is the main mean for us to calculate non-trivial integrals. So we're looking for the composite part. And we have the function 1 over x that is plugged inside the exponential function. So a natural thing to try is to pick u is 1 over x. Because the derivative of 1 over x is negative 1 over x squared, we get for du negative dx over x squared. Notice that we have dx over x squared inside our integral, so we're going to replace it by negative du. And then the other part is e to the u, so that our integral can be rewritten negative integral of e to the u du. And the integral of e to the u du is just e to the u up to a constant. So we obtain negative e to the u up to a constant. And because we're looking for an antiderivative of the function e to the 1 over x divided by x squared, we look for this antiderivative as a function of x. We substitute back the value of u in terms of x, and we obtain negative e to the 1 over x up to a constant. Finally, we want to integrate e to the x multiplied by sine of e to the x. Again, we have a composite part, which is e to the x plugged inside the sine function. So that means e to the x is a natural choice for u, and then du is simply e to the x dx, because the derivative of e to the x is itself. So we have e to the x dx in our integral, that's du, and then we have sine u. In other words, this integral can be rewritten integral of sine u du, and an antiderivative of the sine function is negative cosine, so we obtain negative cosine u up to a constant. And to write the antiderivative in terms of x, we plug back the value of u and obtain negative cosine of e to the x up to a constant. Now turn to the next video to see a little bit more about exponential and logarithms. We're going to review a little bit of algebra associated with these functions.